This is Ms. Black. This is Open Campus for College Algebra, and we're now moving into Module 12. We saw in Module 11 a new equation, exponentials, and we learned how to solve them and saw some real-life application of it. Now in Module 12, we're going to meet another new equation. Okay, don't get scared. It's new. You've probably never seen this equation before if you came through the developmentals 097, 098, 099. Okay, unless you're in an advanced math class in high school, this is going to be a new equation. Again, new doesn't mean hard. It just means a little bit new to you, so it's going to take some time to practice. So let's go up to the whiteboard because I want to discuss with you the connection between what you've learned and how we're going to relate it to this new equation. All right. If you look up here at the whiteboard, I have 3 equations put up here. They're nothing more than good old arithmetic equations, but they are equations. This is a first grade arithmetic equation. 5 minus 3 equals 2. So what operation did I say? I said minus, which is subtraction. Every operation we know in math has an equal, according to Please Excuse My Dear Aunt Sally. Remember that famous phrase? P-E-M-D-A-S? So if we say subtraction, we know it's equal as addition. Well, what that means is you guys could rewrite this as an addition statement. But I don't want you to move the numbers. The numbers have to stay where they're at. So the 5's got to stay here. The 3's got to stay here, and the 2's got to stay here. To write that as an addition statement, don't you agree? 5 minus 3 means the same thing as 5 plus negative 3? Yes. So what we learned is every operation has an equal or an inverse. They go together. Here's a third grade math equation. 100 divided by 2 is 50. True statement. I want to rewrite that. Now I said the operation division. What operation is equal with division? You're right, it's multiplication. So we're going to rewrite this as a multiplication statement. But you can't move the numbers. The 50's got to stay on the right. The 100's got to stay on the left. So I'm asking you to rewrite this. 100 divided by 2. Doesn't that mean half of 100? I didn't move the numbers. The 100's on the left, the 2's on the left. The 2's still in the denominator. The 100's still in the numerator. I'm just showing that that statement and that statement mean the same thing. These 2 equations are equivalent, because multiplication and division go together. They're inverses of each other. Okay? Here we go. Here's a 7th and 8th grade mathematical equation sentence. The square root of 25 is 5. It's true. I want to rewrite it with its equivalency. Well, if you look at Please Excuse My Dear Aunt Sally, your order of operations, this square root goes under P, because that's what P means, any symbol. Symbols have equals. Their equal is an exponent. So we've already discussed in college algebra what exponent means square root. Very good. It means the exponent 1/2. So instead of me writing the square root of 25 is 5, I could write 25 to the 1/2 is 5. So what I want to show you here is every operation has a buddy, an equal. And that means you can rewrite every equation 2 ways and they mean the same thing. These are equivalent. These are equivalent. These are equivalent. So now what's going to happen today is we're going to learn about a new equation. It's got a buddy it's equivalent to. And it's equivalent to what we talked about in Module 11. If I have the equation 2 cubed equals 8, I could rewrite that as another equation that means the same thing. Every equation with an exponent can be rewritten as a logarithmic equation. Now that's a big word, logarithmic. We're going to abbreviate it short. We're going to use log, L-O-G. So I can rewrite this equation as log base 2 8 equals 3. Now I know what you're saying. I don't have a clue what that means. It's okay. What I want you to know right now is every equation that's written with the word log, we're going to be able to rewrite looking like this, an equation with an exponent. And don't you understand that? Yes. The reason why we can rewrite it is because logs and exponents go together. According to Please Excuse My Dear Aunt Sally, they're inverses. They go together. Just like add and subtract go together. Multiply, divide go together. Square roots and exponents go together. So what I want you to notice is the whole topic about today is there's a new equation on our sheet. It's called the log equation. You're not going to like it, neither am I. I'm not going to understand it, neither are you. It's okay. We can rewrite it as something we understand because every equation written with this word log can be changed into this equation. And we understand 2 cubed equals 8. So the first thing I have to do today is teach you how to do that conversion. How do you rewrite a log equation to an equation with an exponent? So we're going to go to our notes. We have 3 examples here. These are all log equations. Why are they all log equations? They obviously have the word log in them. You don't understand them, that's okay. I'm going to help you make sense out of them. And all I got to do is teach you a trick, how to change these equations with these word logs into an equation with an exponent. Now, there's several ways to do this. I could tell you to go to your book and memorize the formula they give you. But you know what? We all know formulas don't always work. Why don't we learn a quick way visually to use our eyeballs to change this equation? And I'm going to show you how to do this. If you look at my exponential equation, this is read base 2, I have an exponent of 3, and this is the answer. So I have a base, I have an exponent, and I have an answer. When I read a log equation, listen to how I read it. Log base 2. So in a log, that little subscript is the base. Log base 2, 8 equals 3. Okay? What I want you to notice is every log equation has a base because when you change it to an exponential equation, it has to have a base. Okay? In this log equation, the exponent's here because the exponent was our 3. And right next to the word log was the answer. So what we're going to do is what I name this myself. You're not going to find it in the book. You're not going to find it in Google. It's called a swing. We are going to swing to make our equations that look like logs into these equations that look like exponents. Okay, if you took Miss Hardy at Bipsy, she calls it swirling. It's a visual way to mark the equation to get it to go from here to here. So the first thing you're going to do is because an exponential equation has to start with a base. When you look at a log equation, what is your base? Your base is always the subscript. So you put your finger on the base. So when I swing, which we're going to be swinging for this whole module, you start with the base, which is the subscript. And then the way you're going to make this visual swing is you're always going to move towards the equals. So here I'm at the base. To move towards the equals, will I go right or left? I would go left. This is what I'm calling a swing. It is this thing right here. It is a loop. It tells me the order I'm going to write my information, my terms. So to swing, you put your finger on the subscript and you move towards the equals. Now what happens here is we want to rewrite this equation so we understand what it means. So what's the base? 7. If you follow the loop, the next thing that comes is the 3. The 3 is the exponent. Then you put an equals, and what I'm pointing at is this x. That's how you rewrite a log equation to an equation that has an exponent, to something you understand. Okay? You can sit here and memorize base, exponent, answer, but you still got to do the visual, the moving. What we've done is we eliminated, we got rid of that word log. We used the other 3 terms, and that's what you want to do. You always want to take an equation with a log and get rid of that word. It doesn't make any sense. You don't even know what it means yet. So to get rid of it, put your finger on the subscript, the base, and if you always go towards the equals, you'll know who the exponent is and what you're going to equal. Now everybody look at this. Do you understand 7 cubed equals x? Sure you do. That means x is 7 times 7 times 7. And that's the goal, to make an equation you understand. Every log equation you can change into an equation with an exponent. And that's what we want to do. And I give it a cute name. I call it the swing. So let's try the next one. Here's my log equation. 2 equals log base b 25. Okay? To swing, you start at the base. What's the base? It's the subscript b. We always go towards the equals. So I go to the right or to the left. I would go to the left, and I'm going to make this loop. That just gives me a visual to figure out what order to put the terms in. I started at b, the base. If I follow the loop, 2 comes next. That will be the exponent. And it's going to equal what I'm pointing at, 25. So your equation that you don't understand now becomes something you do understand. B squared is 25. Do you all understand b squared is 25? Sure you do. You should think back, that's way back in the beginning of modules. That's a quadratic equation. It has a square on it. All right, let's do the last one. I have log base 4, 26 equals y. I don't understand that. So I'm going to convert it to something I understand. I put my finger on the base, which is 4, the subscript. I move towards the equals. This time, to move towards the equals, I'm going to go to the right. So this is what the swing is going to look like. I'm never going to point at the word log. Remember, the whole goal here is to get rid of the word. We're getting rid of the word. This is the order I'm going to write my new equation. I'm going to write my base 4, going to follow my loop. Next comes my exponent y, and it's pointing at 26. And that equation I can understand. 4 to some exponent is 26. So that's the important lesson of this whole module. That we're going to be dealing with these log equations. We're not going to like them because we're not going to understand them. So you know what? Let's make them something we understand. Let's change it to an exponent equation. So every log equation can be changed into an exponent equation. They're inverses, just like add and subtract, multiply, divide, roots, and exponents. So far, so good? Now, the way it happens is they can go both ways. I can now give you an equation with an exponent and ask you to change it to a log. So let's look at those examples. I have 3 of those I want to look at on your notes. This is example 2. Okay? 2a is 2 to the 5th equals x. And then we have 2b, 27 equals b cubed. And 2c, e to the y equals 33. All right. I like those equations. I understand them. They all have exponents. But you can change them to log equations. And I know you're probably thinking, but that's silly. We're never going to use that. Believe it or not, we are going to use it later on. So, to change it to a log equation, the first thing you do is got to write the word log. And the abbreviation is log. Okay? So if it says convert these to log equations, just like you write adding and subtracting, multiplying, dividing, you write the word log. Now, we said every log gets a subscript, and the subscript is the base. Well, you can look up here. What's the base when you write 2 to the 5th is x? The base is 2. So we can still put our finger on the base, and then we could still do the swing. If you move towards the equals, there's your swing. So now you know what's going to come after 2. After come 2 is going to be x. So after the word log, we're going to write x. And it's going to equal what we're pointing at, 5. Now, an important part about writing a log equation is the only thing that should be in the subscript below is the base. This word log, this x, and this 5 are all in the same line. So be careful when you type it in or write it, that you write it correctly. But all you got to do is swing it. So you could swing to make it a log. You could swing to make it an exponent. So let's do this one. We're going to write a log equation. Who's the base here? Well, the base has got to be connected to an exponent. Here's the exponent, so this is the base. The base is b. If you move towards the equals, we're going to the left this time. So the base is b, that's your subscript. If I follow my loop, my swing, I hit 27, and it equals what I'm pointing at, 3. That's your equivalent log equation. Let's do the third one. What's the base in e to the y equals 33? The base has got to be connected to the exponent. The exponent's y, so this must be the base, e. If I move towards the equals, I'm going to go to the right. So there's my swing. So I'm going to write log log. I'm going to put base e. What's going to follow is the 33, and it's going to equal y. Now what's going to happen is when you type in log base e, it's going to mark you wrong. And you're going to say, why is that? Well, really, guys, if you look at a calculator, here's back our calculator, our friend. You're going to find out today there's not one button for log, there's 2. The first obvious button is log, which I have right there. But there's another button for log underneath that says ln. And if you look at ln right above it, what letter is above it? Ah, there's that e. So what happens is, if you have base e, there's a special button on a calculator. So you will never see them write log base e. That really stands for ln. So this equation will be written ln 33 equals y. So just so y'all know, there's not one button for the word log, there's 2. You don't ever have to worry about using the ln symbol for log unless you have base e. If you have any other base, you'll use log. But when you convert this to a log equation, if you write log base e, they're not going to take that. That's really ln. Okay? So now we understand they can convert back and forth. Now we're going to use this fact to actually solve some logarithmic equations. Let's look at our notes. All right? So in our notes, we've done example 1 and 2. Now we're at example 3. Example 3 says solve these equations. If you look at all 4 of these equations, they all have what in common? They all have the word log. Well, that's going to be a problem. If you don't even know what a log is, how are you going to work an equation that has that word in it? So we just learned the most important fact with logs. Every log equation can be changed into an equation with an exponent. So what we are going to do with all 4 of these equations is we're going to do a conversion. We are going to swing them, as I say, my little slang word, into an equation we understand. And that's the goal of this whole module. If you don't like something, you change it into something you understand. All right, let's go back to the whiteboard and try these. All right. So if you all look carefully, I have 4 equations. They're all log equations. They all have the word log. I don't understand what a log is. I haven't explained it to you. Don't worry about it. All I need to know is you can convert them. Every log equation has an inverse. It has an equation it equals, and that's an equation with an exponent. So Ms. Black's going to tell you we're going to swing all these. So to swing, you put your finger on the base. Who's the base? 3. We go towards the equals, which would be to the right. This equation is going to become 3 squared equals x. Follow the loop. 3, 2, x. Now, I'm going to flip that. That's really x equals 3 squared. First of all, impress me. Out of all the modules we have done, what type of equation is that? It's x to the first power. This is a good old linear equation. What's the solution? Well, we all know 3 squared is 9. You just solved a log equation. Isn't that wonderful? That equation really means this, and we understand this. Let's try the next one. I have log base 3, 27 equals x. I don't want a log equation. Put your finger on the base, 3. Go towards the equals. That would be to the right. So this is going to become 3 to the x equals 27. Watch my finger. 3x 27. What kind of equation is that? Is that linear? No way. The x is in the exponent spot. This is what we learned in Module 11. This is an exponential equation. So now I want you to notice when you take a log equation and swing it, you're not always going to get a linear equation. You're just going to get an equation that you've already learned how to solve. And that's a beautiful thing. We're going to go back to all these equations we learned how to solve. All right? To solve an exponential equation, we said in Module 11, we need the bases to be the same. What's the base here? 3. 3 is prime. We can't do anything with it. 27, we all know, if we go to the side here, is 9 times 3. 9 is 3 times 3. So 3 times 3 times 3 is 27, which is 3 cubed. Look familiar? Should. If the bases are equal, then the exponent's equal. So on the left, the exponent's x. On the right, the exponent's 3. There's your solution. You just solved the log equation without understanding what a log is, because you change it to an equation you know how to work. All right, let's look at the third one. Log base x 8 equals 3. Don't understand that. So I'm going to put my finger on the base. I'm going to move to the right towards the equals. So this is going to become x cubed equals 8. X 3 8. It's not linear. It's not x to the first. It's not quadratic. It's not squared. It's a polynomial equation. It's x cubed. We've already seen these. Now this one's easy to solve because there's nothing to move. The opposite of cubing is to do a, you got it, cube root. Cubes and cube roots cancel out. X equals cube root of 8. What number can you multiply 3 times to give you 8? Very good. 2. Can it be positive and negative? No way. The only way to multiply to make a positive 8 3 times is a positive 2. You just solved the log equation. Okay, our last one. It's a log equation. It's got the word log. The base is 4. I'm going to move to the right. There's my swing. So I'm going to write base is 4. My exponent is going to be a 2. And it's going to equal not the x, not the 3, all of it. All you're doing is getting rid of the word log. That's all we're doing by doing this swing is getting rid of the word log. Now, do we really need to keep the parentheses around the x minus 3? No, because there's an invisible number of 1 here, so I can drop those. Okay, impress me. What type of equation is it? No, it's not quadratic. That's not x squared. That's 4 squared. What's 4 squared, y'all? That's 16. If 16 equals x minus 3, don't you agree that's a linear equation? It's x to the first power. You all know how to solve that. Add 3, add 3. X equals 19. So, today's lesson wasn't really bad. You just solved a new equation that you never saw before by doing a swing. But wait, we're not done. Go back to your notes, please. All right. Now that we solved equations, look at our next set of examples. I have 6 examples here. Do they look like equations to you? No. And that's where the problem is. These are not equations. These are expressions. And the directions say evaluate. Evaluate means find their answer, their value. Well, you're probably thinking, well, can I go to the calculator and use that button? No, not yet. And we're going to talk about that why in a couple of minutes. So the problem here is we want to evaluate all of these. All these expressions are in log form because they all have the word log with them. I don't see a point in teaching you anything new. I've taught you one concept so far in this section, and it's if you have an equation with the word log, you can change it into an equation you understand. Now I know that these are not equations. So what I'm going to do is show you a trick. And this trick is not mentioned in the textbook. It's not mentioned in your notes. It's a trick that I think is a lot easier than trying to teach you something new. So if you would all please, let's go back up to the whiteboard and let's talk about this. All right. So if you look here, people, I have 6 log expressions. I know when you read these out loud, you have no clue what the answer is. So what the first thing I'm going to tell you to do is you can't swing them. Because if you put your finger on the base, you're supposed to move towards the equals. Well, there's no equals. Well, we're going to fix that. You can rewrite every single one of these as an equation. Did you hear what I said? You can rewrite every single one of these as an equation. All you need to do is put an equal sign. But you know if you put an equal sign, it's got to equal something. Now, look at me. They're not quadratic. You don't set them equal to 0. You don't know what they equal. So here's a beautiful thing. In algebra, if you don't know what something is, what do you let it be? That's right, you let it be a variable. You don't know the answers to any of these, so we're going to say it equals x. Now, you've just made these all log equations. And if you make them all equations, now you can do the swinging. You can convert these all to something you understand. And that's how I want you to do this. I do not want you to read what it may say in your book. This is an easier method. If you know how to swing a log equation, you could do this whole module. So now that I made them equations, I'm going to put my finger on the base. I'm going to go to the right. Put my finger on the base, go to the right. Put my finger on the base, go to the right. And so on, and so on, and so on. I'm going to rewrite all 6 of these log equations as equations with exponents. So my first one would be 10 to the x equals 100. My second one's going to be 3 to the x equals 3. My third one's going to be 8 to the x equals 1. My fourth one, 7 to the x equals what it's pointing at, 7 to the 8th. My fifth one, 7 to the x equals square root 7. And my last one, 36 to the x equals 1/6. So instead of trying to teach you something new, I got one concept you need to know how to do. If you have a log equation, swing it. If it's an expression and it's not an equation, just say equals x. I don't know what it is. Now that they're swung, we can now solve them. These are all what type of equation? Well, if you look, all the x's are in the exponent spot. So these are all now exponential equations. And this is from module 11. So do you see now why the modules 11 and 12 go together? And because these are all exponential equations, what must be the same? The bases. Now, if we look at the first one, it says 10 to the x equals 100. I know probably all of you can guess at what the answer is. But to prove it, let's do the work. Let's get the bases to be the same. The base on the left is 10. Can you factor 10? Well, you can. What does 10 factor to be? Well, it factors to be 5 and 2. Do you want to represent the base as 2 different numbers, 5 and 2? No. So we're going to be stuck with that 10. The 10 is going to stay. What we can do is rewrite 100. 100 is 10 times 10, which we know is 10 squared. Now that the base is the same, you have your answer. What's your answer for x? X equals 2. See how nice that was? The second, 3 to the x equals 3. Well, that one we have no work to do. The bases are the same. If the bases are equal, then the exponents are equal. Well, here's x in this exponent spot. What's the exponent here? Very good. It's understood to be 1. So that solution is x equals 1. All right, the third one. 8 to the x equals 1. Are the bases the same? No. Now, we know we could factor 8. 8 is 4 times 2, and 4 is 2 times 2. So we all know if you multiply 3 2's, or I could write that as 2 cubed, that would be 8. So we'd have 2 cubed, we have an x, it stays in the exponent spot, equals 1. Now, we got the base on the left side reduced. Can we do anything at the right side? No, 1 can't be reduced. It's in lowest terms. So now we got a problem. The rule is you're supposed to have the bases the same, because if the bases are equal, then the exponents are equal. We can't get the bases to be the same here. There's no way. But that's okay. This is one of these things where you just got to know off the top of your head. It's a straight definition. And what you got to remember is from algebra, what exponent do you put on a base that always spits out a 1? The only exponent you put on a base that will spit out a 1 is the exponent 0. That's a straight definition from algebra. A base with a 0 exponent is 1. So you're right. Even if you try to get the bases the same, you can't. You've got to understand, if an exponential equation equals 1, that means the exponent had to be 0. 8 to the 0 is 1. Okay? The fourth one, are the bases the same? They sure are. 7, 7. So then what's this exponent got to be? Very good. It's got to be 8. Now, the fifth one, tricky. The base on the left is 7. The base on the right is square root of 7. That don't even sound alike, so they're not alike. Can you do anything with 7? Nope, 7's prime. We have to leave the left side. But on the right side, this is where definitions come in. We all know we can rewrite a square root with an exponent. What exponent means square root? It means the 1/2. Don't you dare write here 7 squared. Does 7 squared make a square root of 7? No. 7 squared would be 49. So you got to know a square root symbol can always get exchanged for the exponent 1/2. Now are the bases the same? Yep, they're both 7s. So the missing value for x is a 1/2. And the last one, I got a base 36 and I got a base 1/6. They're not the same. We know we could factor 36. 36 off the top of your head is 6 times 6. What's 6 times 6? That would be 6 squared. So do you agree we could replace 36 with 6 squared? But we got to leave the x up there so it's connected by multiplication. Now, is 6 exactly like 1/6? No, but we already talked about this in Module 11. We could take this fraction and flip it, bring the 6 to the top, the 1 to the bottom. And now they would both be 6s. But when you flip a fraction, whatever exponent's connected to that fraction is going to change. Now you're going to say, well, Miss Black, there is no exponent. Sure there is. There's always an exponent. There's an invisible exponent of 1 on that 6. So when that 6 flips to the numerator, that exponent becomes negative. So we've already talked about that in Module 11. Now, once the bases are equal, the exponents are equal. So if 2x equals -1, we could divide by 2 and get x equals -1/2. So what we saw here is we saw if I give you a log expression, don't flip out. If I give you a log expression, make it an equation by setting it equal to x, because you don't know the answer. Once you set a log equal to something, you can swing it to make it with an exponent. Now we have exponential equations. We understand those, and those are easy to solve by getting the bases to be the same. So far, so good? All right. Now we're going to have some fun and use our calculator, our last part of this module. So let's go back to our notes. All right. In your notes, on your calculator, there are 2 different buttons for log, LOG and LN. And now I'm going to explain why we have 2 buttons. They have to do with the bases. There are really 2 different logs we use in the real world. There is a common log and a natural log. Common means what we use the most. And the definition says here, a common log is a log LOG. And it has base 10. So everybody go to your calculator and find the LOG button. Okay, do you all see your LOG button on the calculator? All right, if you look very closely, do you see on that LOG button a subscript, a base? You should not. It is understood to be base 10. Now, how are you going to remember that? Well, look above the LOG button. What do you see above it? Don't you see 10 to the x? Very good. So you have to know that if we use an LOG button, it's understood to be base 10. So the only thing you can use your calculator for that you type in is if it's LOG base 10. You can't type in LOG base 2 using the calculator. You can't type in LOG base 5 using the calculator. You can only use base 10. And you're never going to see the base. It's going to be understood to be there. Just like you never see the coefficient of 1. It's understood to be there. So it's important that you know that. Now, the other log on your calculator is ln. That's natural log. And if you look above it, what's its base? It's base e, because e is that special irrational decimal. So it's very important you understand there are two different log buttons on your calculator based on what base they go with. Now, we're going to do a typing exercise. So let's go to the whiteboard, because we have 6 examples here. Let's get our calculators out. Okay, so to finish up today's lesson, if I ask you to tell me the value of log of 100, I understand when I don't see the base, it's understood to be a 10, which means I can use my calculator. I don't got to swing it to find the answer. Okay? You type what you see. So if it says log 100, you type the LOG button, and then it opens a parentheses. You type 100, and make sure you close the parentheses. So it's very simple to type this in the calculator. You're just going to hit the LOG, open parentheses, type 100, close it, and hit equals. And when you hit equals, what do you get out? You get out a 2. Okay? Let's do the next one. If I want to know the value of log 1, what am I going to type? I'm going to type, hit the LOG button, type 1, close the parentheses, hit equals. I get out a 0. Even if it's natural log, you just use that button. So to type this in the calculator, you're going to hit ln. It's going to open a parentheses. You're going to type 1 and close it. So when you hit ln, 1, close it, and hit equals, what did you get out? You got out 0. This one, to type in ln e, is a little bit trickier. You type what you see. What do we say first? ln. So now I put a parentheses on your screen. Now you want to type e. Remember, to get to e, you have to hit second ln. So we hit second ln, it puts e on the screen with the exponents button. So remember, every time we hit e, we got to type in its exponent. I don't see it, it's understood to be 1. So I'm going to type ln, then I'm going to hit second ln to get the e on the screen, then I'm going to type 1. My calculator opened 2 parentheses, so I got to close 2 before I hit equals, and I get out 1. Now, before we move on, I just want you to understand, I really didn't need the calculator for any of those. I could have been able to look at all of these and got these answers, because I taught you about swinging. And I want you to understand that. In my day, we didn't use calculators because they didn't exist. They weren't out. What I want you to understand, if I write LOG and I don't put a base, it's understood to be 10. If I asked you to swing this, just like I did a minute ago, you would say, I don't know the answer, it equals x, right? 10 to what exponent would be 100? So if you did the swing, 10 to the x is 100. We all know what exponent's got to go on 10 to make 100? 2. So what I want you to notice is every time you hit the log button, this answer you're getting would be the exponent on the base. Look at this one. It's LOG. It's a common log. It's base 10. 10 to what exponent would spit out 1? Well, it would be 0. 10 to the 0 is 1. So if I do the swing, it makes sense. Even if I do natural log, there's no subscript. You've got to understand that's base e. Now look at me. You don't even have to memorize that. Just look on the calculator. LOG has above it 10. ln has above it e. That's their basis. So if I did the swing on this one, if I said, you know what, if I wanted you to swing this one and work it out in your head, I would say e to what exponent would give you 1? Well, the only way to get a number 1 is to put the exponent be 0. Don't you agree e to the 0 is 1? So this answer the calculator is giving out is the exponent on the base. So if you look here, it's natural log. What's the base? It's e. E to what exponent would give you e to the first? It would also be a 1. Because if I did the swing, e to the x equals e to the first. Don't you agree x would be 1? Isn't what the calculator spit out? So what I want you to understand is instead of you having to swing every single one of these to find the answer, if it's a common log base 10 or a natural log base e, you're typing in using your calculator, which I have no problem with. But you've got to understand all these answers you're getting out. This 2, this 0, this 0, this 1 were the exponents you would put on the base. 10 squared is 100. 10 to the 0 is 1. E to the 0 is 1. E to the first is e. Now, these two expressions don't start out with the word log, so you don't type log first. So to type these in, remember we talked about it. We're going to read it. That's what we're going to type. So we're going to type 10 first. Uh-oh, this log of 33 is in the exponent spot. So that's why we're going to need our caret button, and we always put an open parentheses. What's in the exponent spot? Log. So we hit log, L-O-G. It opens a parentheses. We type 33. Because my calculator opened 2 parentheses, you got to close them, both, too. Hit equals, and I get out 33. Now, I'm going to show you something. You could have looked at this and knew the answer was 33. This log is a common log. It's got an invisible base. What's its base? 10. This is a base, right? Because it has an exponent. What do you notice about both these bases? They're the same. They're canceling each other out. So if you have the same base, they're canceling each other out, and that's where the 33 is coming from. Just so you know. Let's do the last one. If I read it, I read e to the natural log 125. So how do I get an e on the screen? I hit second ln. So I type second ln, it puts the e on. It opens a parentheses. What's in the exponent spot? Natural log, so I hit ln. It opens a parentheses. What's behind the natural log? 125. My calculator opened 2 parentheses, so I closed 2 parentheses. I hit equals. What did you get out, guys? I got out 125. Now again, I really didn't need the calculator. If you look closely, this is e. It's a base because it's stuck with an exponent. If you look at natural log, every log has an invisible base. What's natural log's base? E. Because these bases are the same, they're canceling out and they're leaving the 125. So you can use your calculators for natural logs and common logs. But I do want you to understand that you could figure out what the answer is by just thinking. Okay, we have 2 more modules, 2 more sections in Module 12. I'll see you later.